Alright, so next we'll go to AC generator. Okay, so we have learned about DC motor, right? So DC motor convert our electrical energy to kinetic energy. AC generator do the opposite, which is to convert your so-called mechanical energy to electrical energy. So I rotate this coil of wire inside a magnetic field. This will create a electrical current, or we call it the induced current inside the coil of wire. And this coil of wire is connected to the slip ring. Okay, so this slip ring is, of course, there's a carbon brush to connect to the external circuit. Okay, notice that this AC generator is not connected to any battery source. Okay, so this is your load. Okay, or we call it the resistor. Okay, so what does the slip ring do? Slip ring basically move together with the coil. And this slip ring will maintain electrical contact with your carbon brushes to ensure that your induced current that is being induced inside your coil, okay, can be tapped to flow into the electrical load. Yeah, so the electrical current inside this so-called coil can be tapped, okay, so that it can flow out to the load. Okay, so carbon brush are in constant contact with the slip ring. Okay, so these two are the important features of an AC generator. Okay, so let's take a look what happens inside the magnetic field and the coil. Alright, so you'll notice there's a magnetic field and the EMF produced is sinusoidal. So it looks like a sine wave. This EMF being produced is what we call the AC, alternating current, because if you see that there's a portion of graph that is in a positive direction and a portion of graph in a negative direction. The positive and negative just indicate the direction of the induced current flow. Alright, okay, so what happens when the coil is horizontal? So this coil will be horizontal in this particular manner. The EMF will be maximum. So why is that so? Because when your coil is horizontal, the coil will cut the B field. Okay, so the coil cuts the B field. But when your coil is vertical, in this way, right, the EMF induced is actually zero. Okay, because why? Because there's a magnetic field. So we have a coil of wire. And notice that the coil of wire, these are all holes. Okay, this is one big hole because we have a square loop, right? So this is the frontal view of your coil. Okay, so this is actually empty space or hole. Okay, so the magnetic field will just pass through the hole without being cut. Okay, without being cut. So that's why in your vertical orientation, where the coil is vertical, your EMF is induced is zero. Okay, because there's no the coil does not cut B field. Yeah, okay, so that's why. So when the coil is horizontal, let's go back. So the coil is horizontal like this. So there's this portion, okay, this portion cuts the B field. Okay, so notice that this is not a hole. This is actually a coil of wire, a solid wire. Okay, so this will cut the B field. That's why your EMF induced is maximum. Okay, so you need to know which orientation will induce the greatest EMF and which orientation will induce no EMF at all. Alright, okay, so yeah, so that's how you do it. Okay, so what if I apply some changes to the so-called the scenario? Okay, if I double the speed of rotation, I turn the coil even faster, right, times 2 the speed, so the induced EMF will also be double. Okay, the magnitude of EMF will increase, and not only the EMF increase, the frequency of your induced EMF will also increase. Okay, the frequency. So in order for frequency to increase, your period must decrease, right? Okay, because we know that frequency is equal to 1 over t. So you see that your cycle, your new EMF wave, right, the period will become shorter. Okay. So second is, what if I double the number of turns in the coil? I increase the number of turns. Definitely, the induced EMF will also increase. Okay. So induced EMF increase, but the frequency of my induced EMF does not change. The only factor that changed the frequency of induced EMF is actually the speed of rotation. I rotate faster, the frequency will be higher. I rotate slower, the frequency will be lower. Right? Okay. So yeah, so that's second. Third will be I increase the strength of the magnet. Okay. So when I increase the strength of the magnet, definitely the induced EMF will be bigger, but frequency remains the same. Last but not least, I wound coil around a soft iron. Remember, soft iron is our so-called soft magnetic material. So this will concentrate your magnetic field. Okay, maybe I just write B field. Increase the B field strength. Okay, so if you increase your B field strength, it's like changing the strength of your magnet. Yeah, you increase the strength of a magnet, so your EMF will increase, but the frequency of your induced EMF will remain the same. Right, so these are the 4 factors that will affect the induced EMF, but only one factor will influence the frequency of your induced EMF. Yeah. Okay. Alright, so last but not least will be the difference between your DC and AC. Okay, so DC is produced by a battery, your normal 1.5 volts battery. So notice that the voltage or the current is constant and it's always in the positive direction. Means that my current only flows in one specific direction. But for your AC, alternating current, your direction of current flow will fluctuate. Okay, so sometimes it will flow in the positive direction, sometimes it will flow in the negative direction. Right, so just take note of that.